Now let's kind of shift gears and talk about what happens when we boil water. If you think about it, if you want to boil water, then you're just going to take a pot and you're going to put it to a flame or an electric element, and you're going to add heat or energy to the water. And what's going to happen is you're going to start to get some evaporation, as right down here. You add energy, you break down some chemical bonds, and you change some liquid into a gas. But what that gas has to kind of withstand is it has to withstand the pressure due to the atmosphere pushing down on it and the water. If you remember Pascal's principle, we're always going to have the pressure of the atmosphere pressing down on the surface, and that pressure gets put to everything on the surface, over here, and this bubble. And if this bubble just doesn't have enough oomph, for lack of a better word, then the pressure due to the atmosphere is simply going to crush it. So really, when we talk about boiling is actually water trying to evaporate, and we know that evaporation is a cooling process. That's actually water trying to shed off some of that excess energy. If the bubble can survive, then it's going to rise to the surface because it's less dense than the water. And if there's not enough pressure inside of the bubble, then the bubble is going to collapse. And keep in mind, this is going to be condensation, which we know is a warming process and is going to add energy back into the water, so the water is going to continue to heat up. Pretty much what this all boils down to, no pun intended, is we're not going to get bubbles below the temperature that is the boiling point, simply because the vapor pressure just is not quite there. Once we heat up the water, and we finally reach the boiling point of water, 100 degrees Celsius, then the boiling water is actually going to remain in thermal equilibrium. It's going to be 100 degrees. It's never going to be 101 or 102, at least at sea level. And as the water boils, it's evaporating, and so the boiling water is pretty much being cooled as fast as it warms, as fast as it's being heated up. So here we have energy leaving the water, cooling. Again, this is going to be evaporation, and we're adding energy to the water through the heating element. So it's kind of funny to think about it, but boiling is actually a cooling process as the water is trying to remain at 100 degrees Celsius. Now, kind of an interesting aside on boiling water is what happens as we go higher and higher in the atmosphere. We know as we go higher and higher in the atmosphere, the pressure due to the atmosphere goes down simply because there's less weight. So as we go up, the pressure goes down. And if we were to take these arrows and just kind of shorten all of these guys, well, as you start to boil water at higher and higher and higher altitudes, well, there's less and less and less atmospheric pressure on them. Kind of, you can see me canceling the arrows out. And what that means is water can boil at a lower temperature. So if you ever read on a box of pasta that, if you're at altitude that you need to cook the pasta for a little bit longer, now the reason for that is because the pressure due to the atmosphere is going to go down, so that way the water is going to survive at a lower temperature, so the water is going to boil at a slightly less temperature than 100 degrees Celsius. Kind of the flip side to that is well, how do pressure cookers work? Well, for a regular pot, the water can kind of, do its thing, kind of go off like this. But as we go ahead, maybe put a really tight seal on this guy, then we're going to have water that is boiling down here. The bubbles are going to rise up to the surface, and we're going to start to get water vapor up in here. So now we're not just going to have pressure due to the atmosphere, but we're going to have pressure due to all of that water vapor that's kind of trapped in this lid. So now we're adding more and more and more pressure, and these guys have to survive at higher and higher and higher pressures, and so we can boil water at temperatures that are much larger than 100 degrees Celsius, and we can cook things like rice, beans, and vegetables quite a bit faster. Now I can do the opposite of this. I can just take some ordinary everyday water and I can put it into my little vacuum chamber, and I can turn this thing on, and actually what I can do is I can make the water boil at room temperature. What I'm doing is I'm decreasing the pressure, decreasing the pressure, and this is actually why you need to boil stuff longer if you're at altitude. If you go to hiking the mountains in Denver, you have to cook your pasta a little bit longer, a little bit higher up, a little bit less pressure. So you can kind of see that the water is starting to get some teeny tiny bubbles, and now it's almost a full rolling boil. So pretty cool stuff. Now I want to kind of talk a little bit more about melting and freezing and how there's energy that goes into breaking some chemical bonds when we go from a solid to a liquid or a liquid to a gas. Let's just go solid to liquid first. So let's think about what happens when things melt. Here we have a nice solid chunk of water, if you will, chunk of ice. and it's in a nice crystalline structure. And as we add heat to it, we take a ice cube, we add some heat to it, add some heat to it, add some heat to it. What's going to happen is we're causing the molecules to vibrate faster and faster and faster and faster. And at some point, you got these molecules that are kind of wiggling back and forth, just like that. They wiggle back and forth, such that they have enough energy to, break some of those chemical bonds, and melting is going to occur. So going from a solid to a liquid, we need to add some heat to it. And we actually have a special name for that. We're actually going to call that latent heat. Now, freezing is the exact opposite of melting. That's when we go from a liquid to a solid. And for something to freeze, we have to stick something in the freezer. We have to constantly take energy away. And the molecules are essentially going to decrease in their motion. They're going to be sliding back and forth slower and slower. And there's going to be some attractional forces that are going to cause them to bind together, and we can form an ice. So if we had to add heat to go in this direction, we need to take heat away to go in this direction. So this slide may be kind of redundant, but I've kind of said it before. I really care about where the energy is going when we change phase from solid to a liquid to a gas. And I've already said it, but as we go from a solid to a liquid, we need to add heat. Liquid to a gas, we need to add heat. And so energy is absorbed into the liquid, or the solid, when we go in that direction. And energy is released from the material as we work in this direction right over there. So we need to add energy to go from a solid to liquid to a gas. We need to take energy away when we go in the opposite direction. Now, you may be asking yourself, what happens at exactly 0 degrees Celsius when we have the solid to liquid transition for water, or at 100 degrees Celsius when we have the liquid to gas transition for boiling water, so freezing water and boiling water? Well, it turns out that we're going to have more than one phase existing at a single temperature. Let's just talk about condensation and evaporation really quick. We can have evaporation, where we have molecules that are kind of going in that direction. So here we're going to have some 100 degrees Celsius water, and that's cooling it off. We also have condensation, kind of going in this direction right there, and that's adding energy to it. And so we're maintaining a nice even 100 degrees Celsius. You can also make the same argument for 0 degrees Celsius solid to liquids. Kind of the key thing to keep in mind is they're entering and leaving the phases at the same exact rates. An important thing to keep in mind as we undergo a phase transition is it does take energy. It takes energy to go from 0 degrees Celsius ice to 0 degrees Celsius water, and it takes energy to go from 100 degrees Celsius water to 100 degrees Celsius steam. You still have to keep the pot on the burner, if you will. Kind of what's going on is we're transforming one phase to the other phase, and it's either going to absorb or release this creature called latent heat, which is essentially going to be energy that are in the chemical bonds when we go from a liquid to a gas, if you will. This heat that we add is going to represent a change in the order from, say, a more orderly structure to a less orderly structure, say a solid to a liquid, or a liquid to a gas, when that thing is absorbing energy or releasing it in the opposite direction. So let's just go ahead and put all of these ideas together. Let's consider if we had some solid ice. So suppose we're sitting pretty at like some negative 10 degrees Celsius solid ice. And we know that if we add heat to this solid ice, then the temperature is going to increase. And how much it's going to increase is going to depend on the specific heat of the ice, the mass of the ice, and the change in temperature. So as we go ahead and we add heat, then the temperature is going to go up. So if we kind of plotted this, we'd say the temperature is going to go up and go up and up, go up and go up. But then we're going to hit 0 degrees Celsius, and we're going to be adding heat energy, and we're going to add heat and add heat and add heat, but the temperature is not going to go up. The temperature is just going to kind of sit pretty just like this. So here you can kind of see adding heat sitting at 0 degrees Celsius. Kind of what's going on is we're taking a solid and we're breaking down some chemical bonds and we're transferring it into a liquid. Now, how much heat we have to add is going to depend on how massive the ice is, as well as this thing called latent heat, which is kind of how hard it is to break down those chemical bonds. So the heat energy is going to be equal to the mass, in this case, of the ice, and this is going to be the latent heat of fusion. And for ice, that's going to be about 330,000 joules per kilogram. Then what's going to happen is we'll have converted all the solid ice into liquid water, and we're going to have some 0 degrees Celsius waters, and it's going to warm up and warm up and warm up. And again, what's going to happen is we're going to be saying, okay, well, the heat that we add is going to depend on the mass of the water, the specific heat of water, and how much it changes its temperature by. So again, we're adding heat, so the temperature is going to go up. And then we're going to hit the magic number 100 degrees Celsius, and we're going to have to add heat and add heat and add heat, just like this. And the temperature is going to sit there at 100. And what we're doing is we're taking this liquid and we're converting it to a vapor, and so the heat that we added is in this form called latent heat, which is breaking down these chemical bonds, and the exact number depends on how hard it is to break down these chemical bonds. Now, the latent heat for water is about 2.3 million joules per Kelvin. Same thing's going to apply. We're going to say the heat we add is going to depend on how massive it is, and this is going to be the latent heat of vaporization. One thing to kind of keep in mind is to look at the scale of these numbers. The specific heat of water, the amount of energy it takes to raise the temperature of 1 kilogram of water by 1 degree Celsius or Kelvin, is about 4,000. To convert 1 kilogram of ice to water is going to be, well, quite a bit larger than that. To go from a gas or liquid to a gas, it's going to take 2.3 million joules for 1 kilogram. So this is a huge number. What this is really saying is once we have 100 degrees Celsius water vapor, that it's got a ton of energy to it. Where did the energy go? Well, it went into, or it came from breaking down some chemical bonds. So let's just talk very, very, very quickly about the latent heat of fusion. When we talk about the latent heat of fusion, we're going from a solid into a liquid, so it's just the amount of energy that's needed to change from a solid to a liquid, or vice versa. I mean, we'd be taking energy away if we were going from a liquid to a solid, but the amount's still going to be the same. The amount is going to depend on how massive it is and the latent heat. So again, the latent heat of fusion for water is 334 joules. I converted it to grams here, but it's, you can convert back and forth if you wish. So let's just kind of do a quick calculation. Suppose we had 10 grams of water, and we knew the latent heat was 334 joules per gram, and that's going to tell us that's going to take about 3,040 joules to convert 10 grams of water from a solid to a liquid. If we wanted to do, say, 20 grams, 20 times 334, that's going to be 668,000 joules, and that's going from a solid to a liquid. If we wanted to go from a liquid back to a solid, then all we would say is we're taking it away, so we're just going to put a negative sign right there. Now, implications of this is, farmers in colder climates, what they would do is they would put tubs of water in their cellars, and a lot of the energy inside of the cellar would go into freezing the water, and then they would swap them out with unfrozen ones, and that would prevent their jars of food from freezing. Similarly, the latent heat of vaporization, that's when we're going from a liquid to a gas, when we're adding liquid, or if we're taking it away, then it would be a negative. And just kind of converted this guy to grams as well. Let's just do some quick calculations. Suppose we had 10 grams of water, and 2256. That tells us to convert 10 grams of liquid water to solid water, it's going to be 22560 joules, which is quite a bit more than it was to convert 10 grams of a solid to a liquid. If we wanted to do a similar example, suppose we had 20 grams of water, 20 times 2256, then that's going to be equal to 45,120 joules. Very, very, very large number compared to going from a solid to a liquid. And kind of an example of how the latent heat of fusion or vaporization can play a role in your life is if you actually get your hand wet, you can very, very, very briefly touch a hot skillet, and energy that normally would go into your hand is actually going to go into vaporizing the water, and so you're not burned as long as you don't hold it there for